Dear students, during my last video, I have told you about noise. I have also told you about bandpass noise and how this bandpass noise is important for us in communication system. All those things I have explained you in my previous lecture through a video. Now in this class, we will see some more effect of noise on our communication system. Now let us see what is noise in baseband system. Noise in baseband system. And we are doing this only for comparison. What is this comparison? We will see. First, we will study the effect of noise on the baseband communication system. And we'll get one parameter for the reference. Then, we will see the effect of noise for a passband communication system, that is your AM, FM, SSB and all, and we'll compare that parameter with this. That is what we are going to do here. Before this, we need to know what is baseband system. Hope you remember, I have always told you in the class about baseband system. There is something called as baseband and passband. You need to know the clear difference between the baseband system and the passband system. Baseband system is something where you don't do any modulation. Signal remains in its original form, that is in the low frequency form itself. That's called as baseband system. Now, if you want to see what is baseband system, you have the signal and it consists of only low frequency components. Baseband means low frequency. So only low frequency part is possible to get in this through a low pass filter. So what you're going to get here is a baseband signal. So here you get a baseband signal. This is your baseband signal without any modulations, right? Now, the signal which is transmitted is ST, and the power of the signal which is transmitted is represented as ST. Now this is what transmitted. ST is transmitted. Now we all know we are going to study about the noise, right? Noise is added. A noise is added. So we will take that noise as additive white noise. We will take this noise as a white noise. A white noise is added. Light additive white noise, and what you get here is a noisy signal. Signal plus noise together is going to come at this point. After this comes your receiver. This is your receiver. You're going to use a receiver here, and one thing you remember, you are not going any modulation. Your signal is directly transmitted here and added with the noise. And this is what it transmitted, and you are going to receive this. The signal power at the receiver, we will take it as a SI. This is your receiver. Okay. So can you tell me what should be there in the receiver? Receiver should be another low pass filter, right? Suppose if you have a low pass filter here which passes any frequency between 0 to omega m, you need to receive same signal here because you have transmitted the signal in the frequency range 0 to omega m only. Since you have transmitted signal in the range 0 to omega m only, that signal is added with the noise and that is received at this point. The only way to receive the signal is to pass that through another low pass filter with the same cutoff frequency 0 to omega m, and here you get the signal. Now in this context we are more interested on the signal power and noise power, right? That's why we use a parameters corresponding to the signal power and the noise power. So now this is the receiver of interest which receives a noisy signal. Okay. Now the signal power at the input of this is SI. This also has a noise. The noise power at the input of this receiver, we take it as Ni. Similarly, and this is the filter, low pass filter which we have used, which is supposed to remove the noise and get us the signal. And at the output we have signal power, output signal power as S0, and also output noise power has to be N0. And you have to design this filter in such a way, that your noise component N0 is reduced. Now all these things, all these parameters, we need to put it in the form of a signal to noise ratio. I have already told you the signal to noise ratio at the input, signal to noise ratio at the output are all going to matter a lot here. Right. See here at the input of the receiver, you have some component of signal to noise ratio that is called input signal to noise ratio. Similarly, at the output, you have a component signal and noise. There we come out with a parameter called as output signal to noise ratio. The signal to noise ratio plays an important role. Right? So I have already told you that here this SI is equivalent to ST because whatever transmitted signal power only will come here, right? Because we are considering noise power separately here. That means here you have your SI, okay? The SI is equal to ST, right? Because noise power we are considering it separately. Similarly, N0 is the output noise power. I have already told you is the output noise power. N0 is output noise power. Now, if you see this, it's a low pass noise, right? If you see this noise alone, I have told you that the spectrum of additive white Gaussian noise, okay, is flat. I told you, right? If you take this Sn of omega, okay, 0, and if you take this as omega, right, and it has got a flat spectrum, okay, with the amplitude neta by 2. This is what called as a spectrum of a additive white Gaussian noise. I have already told you this in my previous video. Suppose if you pass through this, through a low pass filter of cutoff frequency, okay, omega m or 2 pi fm. If you pass through this, so what you will get? You will get a low pass version of the noise. Yes or no? You get low pass version of the noise. This is 0. This is omega m. This is minus omega m. This is your omega, and this I call it as S n naught of omega. This is low pass noise. This I call it as low pass noise. Right? Now, this is the low pass noise. This is the noise which is passed through the low pass filter, okay, which we have seen here. Right? Whatever noise which is existing here, that is actually after passing through, it will become a low pass noise. Now, what is that? What is the power in this? Right? What is the power in this? Suppose if I want to find out the power in this low pass noise, this is what actually, this is called as power spectral density curve. What we have drawn is power spectral density curve. The power spectral density curve of additive white Gaussian noise, I have already told you here. And this is the power spectral density curve of low pass noise. Now, the power in this output noise, or we say low pass noise, is the area under the power spectral density curve. Right? The power n naught here. Okay. So this is low pass noise. This is output noise, right? So we are passing this through a low pass filter, and then this is what we get as a noise, output noise. And this is the power spectral density of the output noise, which is low pass noise. Now, the power in this is the area under power spectral density curve. Area under PSD curve. So, you have to get the area under this. So, how do you get the area under this? The area under this, let us put it as n naught is equal to integration. I will put it in terms of Fm, okay? Instead of omega m, I will put it in terms of Fm minus Fm 2 plus Fm, right? Okay? I will put it in terms of Fm. S n naught of F into df. Right? So because I am putting it in the form of, this is supposed to be 2 pi Fm, supposed to be plus 2 pi Fm. So okay, we are going to put it in terms of Fm here. Ultimately it is going to cancel, that's why we are not going to put it. So now just calculate this. Okay, this we can rewrite as, you can see this here, instead of writing this as minus omega m minus Fm, which is also minus 2 pi Fm to plus 2 pi Fm, right? So I'm going to integrate. I can write it, this is symmetric, right? If you see the area from 0 to omega m is equal to 0 to minus omega m, right? So if you take the whole context here, if you take the area, we can write it as 0 to Fm 2 times, right? 2 times neta by 2 into df, right? So because the amplitude here is neta by 2, this is actually neta by 2, right? So if I, instead of considering omega m by 2 minus omega m to omega m, I am taking it as 0 to omega m and I will make it 2 times. It is going to give me the same value of integration. So when you integrate this, so what you get is neta into Fm, neta into Fm, right? So we got output signal to noise, output noise. This is output noise. Also, it is called as, I already told you, it is low pass noise. In my previous slide I have told you it is a low pass noise. The power, that is low pass noise power, N naught, is given by neta times Fm. Neta times Fm. Okay, so now we got output noise power. Okay, and you know certain parameter, right? Certain parameter, signal power, input signal power, output signal power. Now let us calculate the output signal to noise ratio. That's very important. So we have to find out ultimately what is the signal to noise ratio you get from the receiver output. That is what we have to calculate, right? Now signal output power will remain that signal input power itself, right? Your signal is existing in that because we are calculating output signal noise power separately. Now output noise power just now we calculated here, substitute it here, that is neta into Fm, right? Now you represent this ratio as one symbol gamma. Right? So we are going to represent this signal to noise ratio, output signal to noise ratio. Okay, that is for the baseband system. See, here we are using baseband system. I told you baseband system means there is no modulation, only the signal is transmitted. Now we are actually studying what is the output signal to noise ratio when the signal is not modulated and transmitted as it is and received. And after receiving it, what is the output signal to noise ratio is this one. Okay, so we are actually calculating the effect of noise when the signal is not modulated, and we are keeping this parameter as the standard for comparing it with, this is a parameter, we can say a standard parameter which is used for comparing other systems. What are those systems? We have studied so many modulating systems like AM, we have studied DSB, SC, SSB and FM. So we are going to use this as a parameter to test this, right? Now you all understood now what is the effect of noise in the baseband system. Now before that, I would like to tell you what is passband noise. I think I already told you during my previous lecture what is passband noise, right? See, I told you that power spectral density of the additive white Gaussian noise, I told you that it has a flat spectrum. Just now I told you 0, this is omega, this is neta by 2, this is Nsn of omega. This is power spectral density of the additive white Gaussian noise. Now suppose if you pass this through a band pass filter, right, you will get a passband signal, right? You get a passband noise, right? Suppose if your center frequency of the band pass filter is omega c, central frequency omega c, and if the lower cutoff frequency is omega c minus omega m, upper cutoff frequency is omega c plus omega m, considering that this band pass filter actually behaves as your modulation system, That's what happens in modulation system. All of you know about it. I have already told you in many classes like this. So now we are considering a passband system here, not baseband system. So in passband system, when you pass this, what you will get the same, only the passband components, right? 0 center frequency, I said omega c. This is omega c plus omega m, and this is omega c minus omega m. This is minus omega c. Same, this is actually neta by 2. This is the power spectral density for passband noise. Hope you are understanding this, right? Okay, I want everybody to know about baseband system and the passband system. See, normally what happens with your double sideband suppressed carrier AM wave, suppose this is your spectrum, okay, of the message signal, okay, I will write m of omega. If the signal is band limited to B hertz, okay, or I will write this as omega m or minus omega m, okay. Now after modulation, tell me what will happen to the spectrum of the modulated wave after double sideband suppressed carrier modulation. So what will be the spectrum? What will be the spectrum? You all know about it. I have told many times repeatedly, right? Suppose if you modulated this signal with the carrier frequency of omega c, you can see that the spectrum will become like this. This is omega c. This is minus omega c. This is omega c plus omega m. This is omega c minus omega m. What happens to the spectrum? It goes into the passband system, right? Your modulation scheme will convert the spectrum into passband scheme. And this is what transmitted. This is what transmitted. I have repeatedly told. So when you receive this signal, okay, first thing what you do is the band pass filter. Why band pass filter? Because you have to receive the signal only in this range, with noise, right? So noise is affected to this, okay. After noise is added, it so happen that this spectrum of your received signal may be flat, because you know you have this spectrum of the noise, additive white Gaussian noise is flat, having flat power spectral density, yes or no, right? It has all the frequency component, right? So now what is received at the receiver is this signal, okay, your transmitted modulated signal plus this noise both together. That's why, since received signal at the receiver, right, the modulated signal which is received at the receiver has all the frequency components because of the noise, but we don't need all those frequency components. That's why at the beginning of the receiver there is a band pass filter. So when you pass this signal to a band pass filter, along with the signal, your noise also will be band pass filter. That's what called as passband noise. The noise which is also undergoing a band pass filter, okay, with the frequency omega c minus omega m to omega c plus omega m. So that is also band pass filter, right? So received signal will be now your modulated signal at the receiver and also passband noise, right? That is what received at the receiver. And we are going to see now, considering a passband system, which is a modulation system, received a signal at the receiver, that is signal plus noise, and that is passed through a band pass filter. Okay, and output of the band pass filter is now a signal which is your signal plus passband noise. Now we are going to see what is this, what is the signal to noise ratio at the output and what is the signal to noise ratio at the input of the receiver. All those calculations we are going to see for AM, for double sideband suppressed carrier, for SSB, and also for the FM wave. We are going to see that individually, right? Now let us see it one by one. So in this lecture, I am going to just conclude with only this, and next lecture we will see about the noise in double sideband suppressed carrier. So we will just stop in this, and next lecture I will just send you about the noise in the practical communication system, which is double sideband suppressed carrier wave. Please watch this video before going into the next video. So before watching this video, you just see the previous video. That's also very important.